All right. Yeah, welcome to BaseNet review session. We're just going to be talking about BaseNets and then doing some problems. I plan to talk for maybe, I don't know, 10 minutes because there's a bunch of different things. And then we'll get into the problems. So yeah, let's start. What is a BaseNet? It's just a directed acyclic graph that's going to capture relationships between like different variables. So we have an example here where like you have variables such as burglary or earthquake. And these variables could take on values like plus b or minus b, etc. And the way you sort of read this BaseNet that I've drawn here, or that I've copied here, is that the burglary or earthquake influence an alarm. So these both can, for example, cause an alarm to go off. And an alarm then can correspondingly cause John to call or Mary to call because it'll like alert them. And so generally, like you can think about these arrows as like a causal relationship for the most part. So that's how I would interpret this. So the defining feature of a BaseNet is that we're going to be storing these local conditional probability tables instead of storing like a giant probability distribution. So like one way to sort of do this would be to store P of B, A, E, J, and M. But that table is going to get larger and larger as you have a lot of variables. So instead we say, okay, what if I instead stored P of B, P of E, P of A given B comma E, and so on. Those are going to be like smaller probability tables that aren't going to grow as much as the number of variables increase. Now, when we make this like declaration that we're only storing these probability tables, we lose something as well, right? We lose the fact we make a bunch of like independence assumptions. And so I guess that actually is the defining property of BaseNets. The defining property is that a node xi is independent of all of its non-descendant nodes given its parents. So given the parents of j, for example, so given a, because a is the parent of j is then independent of all non-descendant nodes. So it's independent of b given a, it's independent of e, and it's independent of m. So that's sort of like the assumption that we're making. And that's why the structure of the BaseNet might be important to figure out like what assumptions you're going to make. So how do we use this property that like a node is independent of its non-descendants given its parents? Well, normally, if I were to ask you to compute like this joint distribution, the way you would do that is using the chain rule. So you'd say like P of B times P of E given B times P of A given all of that times P of J given all of that, and so on. But what we can do with this BaseNet is now simplify a lot of these. So the P of B remains the same, but the P of E given B, well, that's just the same thing as P of E because we're given all of E's parents because it has none. And given all of its non-existent parents, E is independent of all non-descendant nodes. So E is independent of B because B is not a descendant of E. So we can simplify that, and we can do the simplification for every single like probability that we have here. So for example, P of J given A, B, E, well, that just becomes P of J given A because given A, J is independent of everything else in the BaseNet. So once we make that sort of simplification, that leaves us with the fact that in a BaseNet, the joint probability is just the product of the local conditional probability tables that we're storing. I think that's it for an intro to BaseNets. Any questions so far? Okay, so let's now talk about how to use these BaseNets. So the first thing that we can do with BaseNets is inference. And this is like the most important thing because we want to know different probabilities and we want to do it in a way where that's like somewhat efficient so we can take advantage of this BaseNet. So for example, if we want to know like P of M given plus B, there's a couple ways to go about it. One way is to compute the entire joint distribution using the strategy that I told you above, where you can just multiply together all the tables and then sum out each of the variables that you don't care about. So in this case, we don't care about A, E, or J. So we just sum them out, get rid of them. And then finally, we have a probability plus B comma M, which is really close to what we want. And we can just normalize this one to get the desired probability, P of m given plus b. So those are like the 3 steps to do this thing called inference by enumeration. But that's not really very much fun, because inference by enumeration makes you like compute this entire joint distribution. And if you were able to like store this joint distribution in the first place, then you wouldn't really have a Bayes net, right? You're not taking advantage of like anything here. So there's a smarter way to do this, which is variable elimination. And the question we're asking there is like, do we have to wait until the end to sum out everything, right? So we're summing out A, E, and J, and I've expanded out the multiplications that we do to compute the joint distribution. But you'll notice that like this P of J given A, for example, this is the only place where a J appears. So I could totally just move this summation all the way to the right, and only have to make this small computation. And so this is just like, for example, if I had like sum over J of P of J times 5, right? I can just move the 5 outside, and this summation is the same, because relative to the J, this is just a constant, right? It doesn't change with respect to J. So if we just rearrange this, we notice that we can do this a lot better, right? We can compute this thing, which is like a table / a factor with only one variable. And then we can compute the next variable, which gives us a factor with only 2 variables. And if we slowly, like one by one, eliminate a variable, so eliminate J, then eliminate E, then eliminate A, the size of the probability tables that we work with is a lot smaller. And so to summarize, like in order to eliminate a variable, what we do is we multiply all of the factors that are involved that have that variable in it. So for example, to eliminate J, I just need this P of J given A factor. To eliminate, say, E, I need to multiply both of these. So then you just sum out the variable and get a new factor. And that's pretty much the high level. I'm not going to go in depth about variable elimination, but definitely go back to the discussions in the discussion video that we have, because we don't have a problem on variable elimination today. But there's a pretty solid one in the discussion worksheet that we did, and probably in the exam prep as well. And those problems are just usually going to involve like, what's a good factor ordering, right? That's a common thing that you can see. So like, in what order should we do this kind of multiplication and summations such that we get small tables? And then you could be asked like, what's the largest CPT that's generated, conditional probability table, when you do this. So yeah, you can take a look at another worksheet if you want to go more in depth about this. And the final thing I'm going to talk about before we start the worksheet is independence. So we've talked about like how to compute a particular probability, but we also might want to know like what our Bayes net structure really means, right? What is the relationship between 2 different variables? So in order to reason about an arbitrary question like, is X independent of Y given all of these Z's, right? We use something called d-separation. And to build up to that, everything with independence, for the most part, can be thought of in terms of just triples. So these are probably things that you've seen in lecture, but you can reason about entire paths between 2 Bayes nets by breaking them up into triples. So let's take a look at a couple of these triples. So you can have either active triples. An active triple means that the like side nodes are dependent, or are not guaranteed to be independent. Sorry. Yeah. So in this case, like X is not guaranteed to be independent of Z. In this other case, again, X is not guaranteed to be independent of Z. Whereas on the right side, X is guaranteed to be independent of Z. And so just to get a bit of intuition, this one is called a causal chain. And the way you can think about it is X can influence Y, and then Y can influence Z. But if you now block Y, and you say, we already know Y, then X doesn't have a path to influence Z anymore. So then it becomes inactive. And a very concrete example would be like, if rain causes the ground to be slippery, and the slippery ground causes you to fall, if you condition on the fact that it is slippery or it's not slippery, in that universe where it is slippery, rain and falling are not really related. So that's what we're saying here. And you have a bunch of these different triples, and we're going to use these to reason about d-separation. So in a larger Bayesnet. So d-separation is really a quest for an active path. Now, what does that mean? Well, if we find one active path between two nodes, x and y, then we can say that x and y are not guaranteed to be independent. And the way we go about this formally is we first shade all the observed nodes, so z1 through zk. Then we look at all the paths from x to y. For each path, we want to see, is this an active path? And a path is active if all of the triples along that path are active. So like if I had some longer path, I don't know, like very simple like this, then there's two triples in this path from x to y. There's this triple and there's this triple, and both of these are active because they're just simple causal chains. So then this is an active path, and x and y are not guaranteed to be independent. So if we find one active path, just one, we're good. And if there's anything, any inactive triple along a path, so for example, if I just block this, then even though this triple is active, this triple is not active. And so x and y are guaranteed to be independent. So we will do a question on this in a minute. Problem asks, this algorithm is to find paths of influence. Yeah, we're looking to see if x has a path to influence y, and that would be called an active path. So let's start with just doing a problem on this Bayesnet. So if you have paper, try to draw this, and then try doing part A with 1 and 2. So the first part is just going to be, what are the conditional independences that are enforced by this Bayesnet? So what are things that are guaranteed to be independent? And I've pasted the triples here, so you can reason about them. So let's take like 3 minutes to try to do this one. And if you have questions like as you're doing a particular problem, or you can put them in the chat or just ask. All right, so let me go over this one. So we're going to select all the conditional independences. The first one, A independent of B. This is not true because there's an arrow from A to B. So this path, even though it doesn't have any triples, you know that like this BaseNet has some table P of B given A. And like there could be anything in that table that makes it so that like, for example, P of B given plus A is not equal to P of B given minus A. So whenever there's a direct edge between two nodes, they are not guaranteed to be independent. Next one, A is independent of C given B. We can just sort of look at the paths. So the first thing to do is like shade B, right? So I shaded B. The next thing to do is enumerate all paths. So let's see. There's one path like this. What are the triples in this path? Well, the first triple that I see is this triple. And this is called a common effect triple. And you'll notice that that one is inactive. So therefore, this path is inactive, right? There's no way to go along this path and influence C because it's been blocked. The other path is A, B, C, where B is given. Now this actually is an active triple. So we've successfully found an active path. So this one is active. Oh, sorry. I don't know why I shaded it. We found an active path. So that means that A can influence C potentially. The next one, D is independent of C given A and B. So let's shade A and B, and let's look at both the paths. So there's this path, which is a causal chain with the middle node blocked. That one is inactive. It has an inactive triple. The next path is this path, and this also starts with an inactive triple, which is a common cause right here. So therefore, since both of the paths are inactive, there's no way for D to influence C given A and B. All right, is D independent of C? Well, no, there's this causal chain, right? So D is not independent of C. Is A independent of C? Well, there's this path, which is blocked because it's a common effect, this one. And there's this other path, which is also blocked because there's another common effect, ADB. So this independence relation holds true. Is A independent of C given D? Given D, there's this path, which is blocked. But this other path, this common effect now becomes active, right? Because the middle node is shaded. And this causal chain is also active. One thing you might be wondering about is like how, like what we do about the nodes on the edges of the triple. So if I had like some triple like this, but this node is shaded, we just ignore them. So only really look at the one in the middle. Okay, is A independent of C given B and D? Given B and D? No, because there's this path active. And then finally, is D independent of C given B? This one is blocked. And this one is not blocked. So both of these triples are active. So therefore, D is not independent of C, not guaranteed to be independent of C. Any questions on that section? Or do people want me to go slower / faster? Yeah, the last one. So D is independent of C given B. So let's enumerate the path, D, A, B, C. The DABC path consists of this triple, DAB. And this one is an active triple, right? Because it's this common cause triple. This other one, ABC, is an inactive triple. That's also an active triple. Because it's a common effect with the effect node. So since both of these triples are active, therefore D can influence C given B. Great. All right, let's talk about the next part. What's the minimum set of edges that we need to add such that the resulting Bayes net could represent any distribution. So in this case, the way I thought about this question was that, like, what are the independence assumptions that we make? And the easiest way to see them is by writing out like the chain rule. That's what I did. But if someone has other ideas, then feel free to let me know. So P of A, comma B, comma C, comma D. Well, normally that's equal to P of A times P of B given A times P of C given B, comma A times P of D given B, C, A, right? And I should have done this in topological order. So let me redo that. Sorry about that. P of A times P of C given A times P of B given A comma C and P of D given A comma B comma C. That's the normal chain rule. The chain rule that we get for this Bayes net is going to be P of A times P of C times P of B given A comma C times P of D given A comma B. So let's look at where we made the assumptions. We said we can multiply A and C together, even though normally we need to use C given A, right? So there's an independence assumption. And how do we fix that? Well, we can make it so that C has A as a parent, right? And then we'll have the table P of C given A. All right, P of B given AC, we didn't make any assumptions there. It's the same exact term. And then finally, P of D given ABC. The assumption that we made there was that we didn't need the C, right? In particular, like D is independent of C given A comma B. And to fix that, we can once again make it so that D now, instead of just having A and B as a parent, also has C as a parent. So we can add this edge. So we could add AC and CD. That's one way we can do it. And in general, if you have a fully connected Bayes net, that can represent any distribution. Any questions about this part, or did someone else approach it differently? All right, let's try the next one, which is now we have like these probability tables about our Bayes net. So we have P of C given A, P of D given A comma B, and C given A comma B. And notice that these aren't exactly like the CPTs that we get in our Bayes net, but somebody sort of just computed them for us. So we have these. And what we're trying to do is get back these tables, P of C and P of D comma C given A comma B. So we want to use these tables and the independence assumptions that we make to reconstruct what these ones have to be. So yeah, take another 3 minutes and think about that question. And once again, you can ask questions as you go if you're stuck on a particular thing. And I've reprinted the Bayes net here. You might benefit from looking at what independence assumptions that we made in part A. I've sent the link to the worksheet if you want to do that. Actually, I decided I'll go over this one a little earlier so we can get to more problems, and we can sort of talk through it as we go. So the first one that we want to figure out is P of C, right? And we'll notice that in our BayesNet, we already have a table P of C. And what that means is that C is independent of all of its non-descendant nodes. So in particular, C is independent of A, right? Given nothing, because A is not a descendant of C. And you can see this in the table as well, right? P of C, like these are both 0.8 and 0.2, and these are both 0.8 and 0.2. So no matter whether A is plus A, the probability of plus C is 0.8. So therefore, we can basically conclude that the probability of plus C is 0.8, right? Because in both of these scenarios, that's what it is. And if it wasn't that way, we can sort of just sum out A from that table, but we don't need to. So this would be 0.8, and this would be 0.2. The other one we're looking for is P of D comma C given A comma B. And we really want to think about like how we use the ones that we already have, right? So what would be ideal is if we can sort of just multiply these together to get this. But can we do that? Well, if we multiply P of D given A comma B, we need to multiply that by P of C given A comma B comma D in order to get what we want, right? I'll pause here in case that's not clear. And to explain it in like other words, if we, for example, just wanted P of like D comma C, right, given nothing, then we want P of D times P of C given D. This is the exact same thing, except we have this like dangling A and B there as well, right? You can just sort of ignore them. So this is what we want. And what we have is this one, but also P of C given A comma B. Can we show that these two are equal? In fact, we can, because we made an independence assumption in our BayesNet. And the independence assumption that we made was that C is independent of D given A and B. Therefore, knowing D or not knowing D doesn't change the probability of C given A comma B. So we can just multiply both of these together and get what we want. Now we can just try to do like one of these and say, for example, if we wanted plus A plus B plus C plus D, then we look at the plus A plus B plus D and the plus A plus B plus C in both of these. And then we multiply 0.6 times 0.5 to get 0.3 for this one. And you can do the rest of them in the exact same way. Any questions about this? Or anything about this problem in general? We're going to go to the next one. Okay, cool. The next one is also about independence. I did say we're going to get a lot of D-separation practice today. This one's kind of fun. We basically have like a structure of a BayesNet, but we don't have the arrows. So we want to draw the arrows in a direction such that all of these independence assumptions are implied. So yeah, take a few minutes and try to reason about the first one. Once again, I've given you the active triples and inactive triples. This is something good to have like pulled up during the exam. And once again, if you have questions as you go, put them in the chat or let me know. So you would shade in nodes like when you were you're looking at like a particular independence relation, like F independent of G given C. So for that one, yeah, you'd shade in C. But for the other ones, there's no evidence given, so you wouldn't shade them in. Yeah, Shreyans, that's right. And problem, a triple is active when this node X can influence this node Z. And a triple is inactive when this node X cannot influence this node Z. In particular, like here, X is not guaranteed to be independent of Z, but here X is guaranteed to be independent of Z, given Y. Yeah, that's right. Okay, so with that, let's try to talk about what these are. Okay, so let's start with A independent of G. How can we guarantee that? Well, let's look at all the paths between A and G. There's just like this one, right? And so in order for this triple to be inactive, right, we want A to be independent of G. There's only one triple with nothing shaded that's actually inactive, and that's this common effect triple. So that's what we need. So let's just make this a common effect. A and G have a common effect of C. So A, G, C. All right. Let's do D is independent of E. How do we guarantee that? There's only like one path between D and E. So therefore, we have to use the same exact strategy of making this a common effect. All right. E independent of F, we see, okay, there's one path between E and F. But there's a bunch of triples on there that we could try to block, right? So maybe one that will give us a clue is actually doing the next part because it relates variables that are closer together. F independent of G given C. So let's shade in C and say F must be independent of G. Well, now we know that like what would happen, right? If we made the arrow this way, then F is successfully independent of G. And if we made the arrow the other way, then this is a common effect with the effect shaded. So F is not independent of G. So therefore, this arrow must be downwards. Now, finally, we have to reason about E independent of F. And so let's once again look at the path. Goes this way. And the triples are EBA, BAC, and ACF. So we know we can't block the ACF triple. So therefore, we must have to block, like, for example, this one, right? And we can block this one by once again saying, making it a common effect. So a common effect between E, A, and B would mean we have arrows like this. All right. Any questions about this one? Yeah, hopefully that cleared things up and you can now try tackling part B. I would draw these on paper if you aren't already. Otherwise, it's very hard to do Bayes nets problems, especially on the exam. I think we might provide you with like a sheet to print or to draw beforehand. So try to do that. Aditi, that's right. For a common effect with nothing shaded, we're saying that the variable on the first thing that's causing the effect is independent of the second thing that's causing the effect. So yeah, we're only making a statement about this variable and this variable. Does anyone have ideas for part B?
I was thinking that for B independent to E, you could use a common effect and draw an arrow from B to A and E to A.
Perfect. Yeah, sure. Let's do that.
And then for E independent to C given D, you could use a causal chain and draw an arrow from E to D and then D to C.
Okay. And there's one more path from E to C. So what should we do about that one?
Um, Isn't the path from E to C through the left-hand side already blocked?
Yeah, I
'Cause-
think it is. Yeah, I think that makes sense then. Let's see. So this
I
edge.
think for the path from B to E, we don't make the assumption for D being known, right?
Yeah. Oh, yeah. That's what I was going to get at. Yeah. So we want to look at this path as well. Because B to E has two paths. Sorry about that. Yeah.
Oh, okay. Gotcha.
So let's look at that one as well. How do we block that path?
You can draw an arrow from B to C. So now you have that extended causal effect chain.
Yeah, great. So this path is blocked because the first triple in the path is blocked. All right, then let's just double check like what the other one was. We had E is independent of C given D. We know this one is blocked because it's a common a causal chain, and the other one is blocked right here. So in fact, this edge can go either way, because either it's a causal chain or it's a common cause. If anyone's confused with these names, I'll label them here. Causal chain, common cause, meaning like this thing causes both of these, and then common effect, both of these. Yeah, all we need is one inactive triple along a particular path to make the path inactive. But we need to do that for all paths problem. All right, so the last one is a lot of work. So let's do the next problem, and then we can come back to this if people want. But there is a detailed explanation on the answer key that we'll post. But you reason about it in the same way. It's really not like that much harder. It's just longer. All right, so the last thing that we talk about with Bayes nets is sampling, right? Because all of these approaches like variable elimination and well, inference by enumeration are very computationally expensive. So sometimes we're okay with getting approximate solutions by just taking samples. And this is a common thing, not just in Bayes nets, but when you're trying to learn like any probability that's hard to compute. And so the way we do sampling is we say, okay, this is the Bayes net that we have. And let's say we want to know something, like we want to know P of like plus F given plus E. What we could do is basically sample every variable. So we could say, okay, the probability distribution of A goes such that it's heads or tails 0.75 of the time, and then tails like 0.25 of the time. And so we'd roll a coin that has that property. And then we'd say, okay, A, for example, happened to be 0. Like that's what we got when we rolled the dice or the coin or whatever. Then we do that for each of the variables, and we are going to go in like a topological order so that all the parents are determined. So for B, we say, okay, let's look at the B given A table and say, okay, what's probability of B given A equals 0? Well, that's going to be both of these rows. So now we're going to roll something and say, and use 0.1 and 0.9 as like our cutoffs. And okay, this one seems more likely. Let's say that's what happened. So then we say, okay, B was 1. And we do the same thing for all of the variables. So let's say this is what we got. And then we say, okay, that's a sample. Now, the samples that we care about are going to be the ones that match our evidence. So all of the ones that have plus E. So the one that I have here, which has like minus E or 0, for example, we really don't care about that one in the first place, but we'd still collect it. And then what we do is basically in these samples, we tally up the number of samples that have plus F and divide by the total number of samples. So we'd say count up plus F, divide by plus F and minus F. And that's how we do sampling. Now, the way that I described to you right now, that's called prior sampling, which is like the most naive way to do things. You sample everything and you keep everything. And then in the end, you sort of just ignore the ones that don't match your evidence. So that's the one we're going to start with in part A. So in prior sampling, what's the likelihood of obtaining this sample? So yeah, take a minute and think about that. Right? Anyone have thoughts? Oh, and this is the probability we're computing, by the way. I don't think it matters right now.
I think it's the one on like the second column, the first one.
Okay, you want to explain?
Yeah, so for the first part, I look for A equals 1. The probability that A equals 1 is going to be 0.25.
Okay.
Then for the next one, there's for B equals 0. Since I know that A equals 1, I'll only look at like the last two columns in that conditional table. And the probability that B would equal 0 given A equals 1 is 0.5. Then continue doing this for the other variables. For like C, looking at the conditional table, conditioned on A equals 1, what's the chance that C equals 0 is 0.7. And then that kind of eliminates the rest of them.
Great. Yeah. So exactly like the coin toss sort of procedure that I described earlier was like, yeah, we go in topological order and then we look at all the probabilities. And we always have a guarantee that we know our parents before like we actually get our probability from our table. So that's great. And you can do 3 of these and notice that this is the answer, but there is an other for some reason. I don't know why we like to throw that in there. But yeah, that's going to be this one. The next strategy that we have after prior sampling is this thing called rejection sampling. So it's not too much different, but if we're trying to go for P of C equals 0, given B equals 1 and D equals 0, then we might accidentally say like, okay, sample A, let's say it's a 1. Sample B, let's say it's a 0. At that point, we say, okay, that doesn't match my evidence. That means the sample is going to be completely useless to me no matter what happens for each of these. So then we say just throw that sample away early instead of completing this. And so that's all we're going to do in rejection sampling. So from rejection sampling, for example, you couldn't produce the sample like plus A minus, A equals 1, B equals 0, C equals 1, D equals 0, whatever, because you just immediately stop when you notice the B equals 0. Okay. But with rejection sampling, the problem that you can run into is like you might just be throwing away like all of your samples. So the next approach that we take is likelihood weighting. In likelihood weighting, we fix all our evidence variables beforehand to be what they're supposed to be. So we say B is always going to be 1 and D is always going to be 0. We then go on and sample like the same way with a slight change. So we say that we want to sample P of B given A, or like when we're trying to sample, we sort of do the same thing. So for B given A, we look at this table and we say, okay, I got A equals 1. And therefore I look at like, sorry, I misspoke. We never do anything for B equals 1. We only look at the variables like that we haven't already fixed. So we haven't fixed C, for example. So we just look in the table C given A, and given A equals 1, we find like what the probabilities are, roll our dice, do the same old thing. But then since we're not actually sampling these evidence variables B and D, we know that some samples are going to be more likely than others. And the way that we compensate for that is we say give each sample a weight. In particular, weight each sample by probability of evidence. So earlier you didn't account for the probability of evidence. And so now you'll weight each sample by the probability of B equals 1 given what you ended up sampling for the other things, and D equals 0 given what you ended up sampling for the other things. And so this problem is asking, what is the weight of this sample A equals 1, B equals 1, C equals 0, and so on. And so we say, okay, what are the pieces of evidence? Well, B equals 1 is one evidence and D equals 0 is the other evidence. So what's the probability of B equals 1 given its parent, A, which is equal to 1? That's going to be 0.5, right, from this table here. So that's going to be like the first thing. And the second thing happens to be 0.5. There's no other option, so I'm just going to circle that one. So we're weighting down samples that are less likely and like giving a higher weight to samples that are more likely to we're more likely to have encountered. I'm going to finish up the worksheet. It is 4 o'clock. Feel free to go if you want. I'll also go over this last part. And if people have questions, feel free to stick around. So the last part is about Gibbs sampling. So this is another way of sampling, because with likelihood weighting, you encounter this problem that when your evidence is sort of downstream your Bayes net, right? So let's say this is our evidence, and these are like the other variables. Then what we end up doing is never actually taking into account the values of our evidence when we're sampling all of these variables at the top. So likelihood weighting doesn't work that well when our evidence is downstream. And in particular, what can end up happening is that you get a lot of really low weight samples because you didn't consider like this fact. So what we do instead, or like another way to tackle this, is something called Gibbs sampling. And what you do in Gibbs sampling is you initialize every variable randomly, like completely randomly. So like, let's say this is 1, 0, 0, 1, 0. And the evidence variables you initialize to match what you want. So this one becomes B equals 1 and D equals 0. Then you choose another variable like at random or through some approach. and you resample that variable. So for example, here, like I have this like initial sample that I've started with, and let's say I want to resample F. In order to resample F, the probability distribution that I look at is the probability of F given all other nodes in the BaseNet, because I have all the other nodes in the BaseNet, right? I have A, B, C, D, and E. And so that's what I use to resample F. So yeah, that's what we're doing in Gibbs sampling. And so let's say we start with this initial distribution and we resample F, as I was saying. What is the probability that the next sample drawn is this sample? So you'll notice that the only thing that changed here was F, because everything else remains fixed. Anyone know how I can compute this probability of F given all other nodes in the BaseNet? And I'll zoom out and show you the BaseNet. Oh. Just on a high level, I guess. Yeah. So what you notice is that F is only dependent on E and D. And in particular, like given E and D, we know that F only has like ancestors B, A, and C. So that's what allows us to do this. We can say that P of F given all other nodes is equal to P of F given E and D. And this is not something that we're always going to be able to say, but we're always going to be able to say that we can just use P of F conditioned on a relatively small number of nodes compared to the size of the BaseNet. Yeah, so in this case, yeah, that's true. So F given E comma D, we can just sort of look at the table, and Shreyan's pointed out it's 0.4. I believe him, so I will circle that one. All right, that's it for this part. Any questions?
I think Shreyan's explained a little bit in the chat, but I'm still a little bit confused of why we could do just 0.5 times 0.5 for part B, the answer that we chose.
Okay, so the two probabilities that he explained we used were the probability of D, which is the first piece of evidence, and the probability of B. And in particular, we did like D equals 0 given its parents, and B equals 1 given its parents, right? We multiply those together. Those are both the probabilities of the evidence. What part are you confused about?
Oh, so we did do that calculation and it yielded 0.5, which is why we just picked 0.5 times 0.5.
Yeah, so this probability is 0.5 and this probability is 0.5. And it's not really a calculation, we just look in the table.
Oh, okay, got it.
Wait, sorry, what was the answer for the Gibbs sampling one again?
I think it's 0.4. Well, that's what Shreyan said, and I can double check in the answer key.
Sorry, I was just a little confused about this though. So it's because we initialize everything. So I mean, after that initialization, which is random, so like it gave us that initialization, and then we resampled F. It's basically just asking what's the probability of F occurring given this initialization.
Mm-hmm.
Okay, that makes sense. Thank you.
Yeah. In this case, it just happened to be that that's equal to P of F given E and D, because F is independent of everything else given E and D, which are its parents.
Oh, was it just coincidence that it was equal to P of F given E and D? Or was that how it was designed?
If you had a more complicated BaseNet, like if you had another variable here, for example, right? F is no longer independent of A. So you'd have to like multiply a couple of probabilities together. It's sort of a coincidence, but it plays to the intuition that you're going to need like only a small number of variables or around your F to make it independent of everything else.
Okay, that makes sense. Thank you.
Cool. All right, let's go over this last part. So take a couple minutes and try to do it if you're interested. And then I'll go over it.
Could you give an example of like the inactive common effect triple? Because I don't really understand that one very well, like what it's like where the independence assumption comes in for there.
Like, do you mean like a story example?
Yeah, I guess that'd be easier.
Sure. Yeah, try to work on this problem and I'll think of an example.
Okay.
Okay, so like an example here would be like you have like some drug one, like say like Tylenol, drug two, let's say like arbitrary, no, let's, I don't know, like cocaine. And then like they both have like some side effect. Let's say they both cause like stomach aches. That's B. And then what you can say is that whether you took Tylenol and whether you took cocaine might be like independent decisions, because you don't know like what relates. You don't know whether you got a stomach ache or not. So there's really they're causing the same thing, but they're not really related, and they might be in real life, but this is what we're modeling. And if you said, okay, now I know that you had a stomach ache, right? Then you can actually say that the Tylenol and cocaine are not independent and are not guaranteed to be independent. And the story would go that like we want to show that P of A given C, A given B is not guaranteed to be equal to P of A given B and C, right? And so in particular, like the probability of Tylenol given that you have a stomach ache and the probability of cocaine given that you have a stomach ache. Let's say what happened is you knew that you like, or the whatever person like took cocaine, right? And they had a stomach ache, right? That's this probability here. Then what you can say that it's probably less likely that they took the Tylenol because like they already took something that explains this stomach ache. Yeah, that's the story.
Okay, that was helpful. So in this situation, then A and C would be independent then.
When I shade B, when you know that there's a stomach ache, then you know that if you took the cocaine, then you're probably less likely to have taken the Tylenol as well, since you took something that explains this stomach ache already. So
okay, so
B and C are dependent, are not guaranteed to be independent.
okay, so it gave you some information about the other one.
Yes, so this is active now. But before we said that this is inactive when B is not shaded.
Okay, and in the inactive case, then then only A and C are independent, right?
Yeah, A and C are independent, exactly.
Okay. Okay, that makes perfect sense then. Okay, thank you.
Great. Yeah, this triple is a little weird to story about as well. So I did my best. All right. So let's try doing this problem. Yeah, what ideas did people have? Let's think about like the independences like individually. So like, for example, like for F independent of G, what could we do?
We could draw the line from G to E and F to E since like we want it to be an inactive path with nothing shaded.
Yeah, that's good. So this is a path and we want to make it inactive. So let's make this an inactive triple. So that's satisfied, or that's not satisfied, but we know that one thing, like this is one thing that we have to do. Yeah, what are other things that we might have to do or can do?
There are also another path from F to G through H. So we probably also want to draw a line from F to H and also G to H.
Yeah, great. F to H and then G to H. Okay, great. Yeah, so that's also blocked. And now there's still other paths, but we'll get to them. Yeah. Cool. Maybe let's try D is independent of E given F. That's an easier one because, or I think it might be an easier one. So D is independent of E given F means we want this path to be inactive as well as this path to be inactive. How do I do that?
Draw an arrow from F to D.
Sure. So that makes this path inactive because this is a common cause. And I think, in fact, this arrow, in this scenario, this arrow could go the other way as well, because this is also inactive. But let's do it the way you described. I think we need it for something else. And the other path is this path here, right? How do we block this path?
Arrow from E to C and arrow from D to C.
Yeah, so exactly what we've been doing with the common effects, right? This is also inactive. All right, so we have a bunch of things filled out. Let's go back to F is independent of B given G. Let's do that one. So given G and not given this, F is independent of B. How do we ensure that? One path is this one, right? We need to block this path. And since there's only one triple, this must be a common effects triple. All right, another path is this one. And since we need to block this one, we need this to be another common effect. Another path would be like, say, like right here, right? And so we need to block this somewhere as well. So one place we could block it is, for example, right here. Or actually right here would be fine as well. So we could maybe block it like this, right? This blocks this entire path. Any thoughts on what the rest of the edges should be?
I don't think it matters what the other two are, because the only one we haven't satisfied yet is F independent of G. Or I mean, the only one we haven't completed is F independent of G, but like looking at it, there doesn't seem to be any paths that are not blocked from F to G.
Yeah, I don't see them immediately either, but I do know that these edges actually do matter. Let's see. So F to G, for example, this path is blocked, this path is blocked, this path is blocked, this path is blocked, and so on. Okay, so that doesn't seem to have any hope. What about F to B given G? Have we satisfied all of those? So this one doesn't matter, this one doesn't matter, this one doesn't matter. I'm not sure. And then the last one was D is independent of E given F. So independent of E given F. So this path is blocked. Maybe we could take a path like this from D to E, right? So we want to block that one. So what must the edge from A to B be?
You need an edge from B to A and then from G to A as well.
Okay, so what does the edge from B to A get us? Oh, sorry, I was asking you.
Oh, sorry. I don't think it does anything else for the other paths from D to E, but the only path which goes from D to E through that edge is the one that goes through from A to G as well.
So like this path?
Yeah. So I think my logic is that that's the only path left that hasn't been blocked to make this independence relation hold. Because if I were to go from D, B, A, C, E, I have the thing from A, C, E, which is already blocking it. So I don't have to worry about anything else from there.
We can block this path. And as you said, if we make an edge from G to A, then we block this triple. And so therefore this entire path is inactive as well. Yeah, I probably missed a couple pieces of logic there, but I think that's the general idea. Any more questions about this?
I actually have a question about the previous question, the problem 1, part B.
Yep.
So for the 3, I was like thinking that can we think it this way, like probability D and C given AB equals probability A, B, C, D, and divided by the probability of A and B?
In this case, that would be, this probability would be, that's right.
Yeah, and then I was like expanding the A, B, C, D, since like it just basically all the nodes given their parents. And then I got like probability of C times probability of A times probability of B given AC times probability of B given AB. And then divide by probability A and probability B given AC, right?
Divided by probability
of A and probability B given AC.
Where'd you get the C in the denominator? Oh, because it's the...
Yeah, because there's like a C is B's back parents. And then like I actually cancel out the probability of A and probability of B given AC, and then just the only two things remaining will be probability of C times probability D given AB, but it's different from what you have like inductor from the probability of D given AB times probability C given ABD. So I was like really curious, like why probability C given AB actually wouldn't be deducted to probability of C, since since C is like the parent node, which don't have any parents.
Okay, so you're saying why would probability of C given AB not be equal to P of C given B?
Yeah, just probability of C.
Yeah. So the reason why this doesn't work is because all we know is that C is going to be independent of all non-descendant nodes. So we know that C is independent of A, but B and D are actually descendants of C. So we don't know that C is independent of anything else. And you might notice that like C and B have an arrow between them. So it's probably pretty unlikely that C and B are actually going to be independent.
I see. Where did I go wrong from my like induction?
I think where you went wrong was canceling out the P of B given AC. Let's see. Wait, did you?
So it cannot be canceled?
Because in this case, we want to sum out over C of P of B given AC, right? Because the denominator should just be P of A comma B.
Yeah.
So I don't think we can cancel it out when it's inside the summation.
Oh, I see. Okay, I gotcha. Oh, I see. Cool.
Cool.
Okay. I see. So if I actually sum out like using this equation, it will be the same probability that you got, right? It'll be the same result.
Do we have all these tables?
I don't think so. Okay. Yeah, then probably the only way we can do is like through what you did. Okay.
I think so. Maybe we can simplify these a little bit, but your general logic is perfectly valid.
Okay, cool. Sounds good. Thank you.
Great. Let me stop the recording.